start with questions on the homework. So I think homework for chapter 4 and 5. So any homework for chapter 4? Any questions? 11, what did that ask you to do? We're in the chapter 4 homework, so this is, yeah, homework number 6 is what I'm talking about.
Number 4? Okay.
3 minus. And you wanted to do qualitative analysis, I suppose?
That was smart. I was thinking about it.
Yeah, so what was step 1?
Steady state.
Find steady states and inflections. So for steady states, you set the derivative equal to 0, which is 3 minus y. So you get y equals 3. That is your steady state. For inflection points, you take the second derivative equal to 0, which is the derivative of the derivative, so that's minus 1, which is never 0, so no inflections. The next thing we do is step 2, which is
Graph.
the stability graph in particular, in which you graph y prime versus y. What does the graph look like here? 3 minus y. It's linear. How's the slope? Negative slope. The vertical intercept is at 3. The horizontal intercept will also be at 3, which is the steady state. So how do we analyze the steady state here? Over here? Arrow to the right, right? Because the graph is above, over here. Arrow to the left, because the graph is below. So this is a stable steady state. So you will go towards 3 no matter what. And so here we usually skip that 4. You draw the solution graph. All right, 3 you only do if you can't figure it out. It'll help you. So here we graph y versus t. And our steady state is at 3. There's no inflection points, and so we just want to worry about the initial conditions. This tells you where to start. So here, you start one at 2. How would it look?
Towards 3.
Going towards 3, so it's increasing. What's our concavity?
Concave down.
Concave down. Has to be down like a frown so you can level off. So no, part 3 would have told you that, but you can sort of see it. If we start at 4,
Concave down.
it's concave up, increasing or decreasing? Decreasing, because you'd have to be going towards 3 no matter what. So ultimately, that's the graph you would get to for the solution. And usually the questions, they go through these and they ask you for these in parts. Part A, find the steady states. Part B, what is this graph? Do the stability analysis. This is the stability analysis. That's why it's called the stability graph. And part 3, determine the concavity, blah, blah, blah. I mean, for our purposes, you can skip that. And then the solution graph is ultimately where you want to get to, where you actually use these two to figure it out. Other questions?
19.
Okay, what does that one say?
y over dt 2 minus y squared, 2 plus y squared,
2 plus
y squared over 1 plus y squared. And then the initial condition is -1.
y of 0 equals -1.
Yeah.
Yeah, so for graphs like these, I mean, we could go through the stuff and graph it, because I think we did learn how to graph this in TOEFL 5, but they actually gave you the graphers. What did the graph look like? Does anyone actually have the textbook?
It looks like, yeah, that.
Yeah, it's gonna be.
And it's increasing towards 0 at the tail.
Yeah, so in this case, they gave you the stability graph, so they did step 2 for you. So they were going to graph. So this was given, so all you have to do really is the analysis on this. So that was done for you, part 2. So part 1 is the something we had to do. What were our steady states? This means 2 plus y squared equals 0, which has no solution, no real solution. And you can see from the graph, it never intercepts the horizontal axis, so there's no solution for that. Because you can't square something and add something and get 0. Add a positive number. And do we have any inflection points?
Yes.
What were the
0.
Well, you can even tell from the picture. Remember, your inflection points will be the max and min, or mins that occur in your stability graph. So here we can know y equals 0 would actually be an inflection point, just by the picture. But of course, you can go through and you can find the derivative of this and set the numerator equal to 0, and then you would eventually get y equals 0. So what's our stability analysis here?
No steadies.
There are no steady states, but can we tell if this graph will be increasing or decreasing? It's always increasing, right? There's an arrow to the right for the whole thing, right? Because it's always above, right? So we know that no matter what, our solution should always be increasing. And from this, we should be able to draw the solution graph. So there are no steady states to put on the map, but there is an inflection point that happens at 1?
0.
0. So 0, that's actually an inflection point. Okay, so if we start at -1, how do you think the graph should go?
Concave up, increasing till 0. And then
Concave up and concave down. Right, so the thing is here, it's sort of unclear what your concavity should be actually, right? There's no like steady state, so no, we have to be this concavity to level off. So you probably have to do step 3, just to make sure that everything is okay. Usually the reason why we can skip this is because we have these steady states that we know, oh, we have to level off to them, so we sort of know the concavity. But here it's not clear. I do step 3. So I know, because there's only an inflection point, 0 is the only thing I have to test around. So I look at G prime times G over here, and I look at G prime times G over here. And so we go to our stability graph, right? And we know the graph is positive over here and the slope is positive. So here, this is positive, positive, which overall is positive. So we know on this side we're concave up when we're below 0. And on this side, the graph is positive, but the slope is always slightly negative. And so the slope is negative, but the graph is positive. And so overall this is negative, so we know we're concave down when we're above 0. So that's why I know here I should be concave up, and then after concave down. It's not clear here because there are no steady states. So in that case, just do step 3 to be sure. Any other questions?
Number 31. You can see the it's like 19.
Oh, it's one where they give you a graph?
Yeah, but I was confused only on part or number C where y of 0 equals 4, like the initial is 4. I was confused because on my part 3 I got concave down, but it would have to, but it's a, I think it's
Okay, let's look at this one. This is,
the y, yeah. So I said, because they tested.
they didn't tell you what the function looks like. They just gave you the stability graph.
Yeah, it was,
So here they just gave you number 2, and you sort of have to figure out everything from that. So, this happens at -2. This happens at +2. I notice I drew this more suggestively than you saw in the picture. What's this? Those are minimums, so they're actually inflection points. It's not as pronounced in the computer picture, but you can clearly see that there's a point where the graph goes down, but it comes back up towards the horizontal. So you know there must be a minimum somewhere here. It looks like it happens around 3. So that's probably somewhere around 3. It's not exactly clear, but around 3. And there's also would be an inflection point at 0 because that's going to be a maximum. So this is a steady state. This is an inflection point. This is a steady state. This is an inflection point. And we can do the stability analysis for this one. On the left, how does it look? Arrow to the left, over here. Arrow to the right. So this is unstable, over here.
Right.
Arrow to the right. Arrow to the left. This is stable. So we'd like going towards 2, but we don't like -2. And now we want to get to the solution graph, which is step 4. Versus y. Let's put in all these guys. So 0 is an inflection point. 2 is a steady state. Roughly at 3, sort of an approximation, is an inflection point. -2, steady state. -3, inflection point. And they gave us 3 initial conditions. One was at -1.5. Another one was at +1.5. And another one was at 4. Okay, so let's start with this one. How would it behave?
Concave up.
So we're between this and that, right? Which means we should be increasing towards 2. So I should be going up. I'm going towards 2, so I know I have to be leveling off here, which means I want to be concave down up here, which means since I passed over an inflection point, I actually want to be concave up here. So that's what that graph would look like. And what about the 1.5? Should be going towards the 2. 1.5 ends up here, should be going towards the 2, but concave down the whole time because you don't pass an inflection point. And the 4?
Concave down to 3 and then.
Right. It's going towards the 2, but it passes through an inflection point. I know to settle here, I need to be concave up, which means I want to start concave down here, and then switch to concave up. there any questions on that? Which part was confusing you, you said?
I just didn't write down the inflection point at 3, and so I was confused because I was having it concave up.
Oh,
But
right,
I couldn't
okay.
approach the steady state without.
Yeah, there were two minimums. If you sort of look at the graph carefully, you realize that had to happen. It looks like it's around 3. So this could be 3 question mark.
It's not a very clear graph.
Yeah. And you also, it doesn't really look like a minimum because it rises so gradually, but you can tell it has to be. Because it was lower over here and then it got closer to the horizontal.
29.
So 29. 29 says C exercises 10 and 23. So it's in figure 4.9. So they also gave you the graph for that. They want to.
They don't want you to do this.
So in 29. 29, they gave you the stability graph. That's a steady state. It doesn't really tell you where it is, but it's before 1 somewhere. And then, in theory, you could figure it out. The graph is, let's see if we can actually solve this. dy dt minus y minus e to the 2y. Let's see if we can figure out where this guy is. So they gave us step 2. Let's go back to step 1. Try to find the steady states and inflection points. Steady state means that I'm going to set this equal to 0. Can we solve that? That's the second. Huh?
Can take it 2 up to the y.
Do ln 2 plus ln.
Or why don't you just
Ln
take
at this
add to
point
it.
is not.
switch that e to y to the other side? And then what I did is I plopped that ey from that side under it, under the 2, and then I multiplied it.
Well,
so
you divide it by e to the minus y, is what you're trying to say.
yeah, basically. That
Which
would
means
be-
multiplying by e to the y. So you end up with 2 is equal to e to the 3y.
Yeah.
Alright? And then you can ln both sides. I wouldn't ln from here because dealing with that minus sign inside an ln is troublesome. So this would mean that 3y is equal to ln 2. So y is equal to ln 2 over 3, which in your calculator, what is that roughly? Well, I know it's less than 1.
I think it left it as ln 2.
1, 2, 3, 1.
It's 0.2. Right. But yes, leaving it like this is fine. This is the steady state.
I did something.
And inflection point means I have to find the derivative of this, which is minus 2e to the minus y
Decreasing.
minus 2 2y, and set that equal to 0. So I can divide by minus 2 on both sides, which means e to the minus y should be equal to minus e to the 2y, which has no solution. How do I know it has no solution? What do we know about the exponential in terms of the signs it takes? the exponential is always positive, right? So this is a positive number, this is a positive number, but then I take the negative of it. So what this is saying is there's a positive number equal to a negative number. Impossible. So I know that has no solution, which is justified by this graph here. There, I don't see any maximums or minimums, so I wouldn't guess there are any inflection points anyway. So now I know there's no inflection points. I have the stability graph. Analyzing this, arrow to the right, arrow to the left, so this is a stable, steady state. There are no inflection points. So now I can do the solution. So the steady state is at ln2 over 3. There are no inflections. Our initial condition, this is for problem 29.
I don't think they gave us.
Oh, they never gave us.
I think
Right,
they
so
wanted you to analyze this.
Yeah, I
In
don't
terms
think
of
we
the-
should know.
Yeah, oh, so it didn't ask you to go very far, but I guess you could do it for fun if you wanted to.
Yay!
Let's do it for fun.
Yeah, well, it's stable, so if you start above here, it's going to go like that. Start below here, it's going to go like that. Okay,
Do it
so yeah, exercises to pay attention to. The cubics are pretty popular on the final. So, like problems 15, 16, 17. That's actually a quadratic, but they write it in that weird form that students always mess up because they don't expand and then refactor it, which is the proper way to approach that. It's like 15, 16, 17. Yeah, things of that. And questions like the one I gave as an example in class where I had y times some, y minus something times y and something times y as well. So those are pretty typical. I mean, you won't see something like this on a final usually. It'll be like a quadratic or a cubic, and if a quadratic does come on, it will come on in a weird form, like in problem 17. So if you wanted to focus on several problems more than the others, make sure you have those down, because more than likely something like that will be the kind of problem that you'll face. Questions on homework from chapter 5?
14.
Someone said number 9, I heard, and 14C. Okay, let's see what number 9 says. Okay, so this is a logistic model, right? I know because they told me the carrying capacity, K equals 300. So for number 9, I know I'm using n prime equals Rn times 1 minus n over K. Part A, they told me R is 0.02 and K is 300, which means that's the equation I'm dealing with. And I want the initial population to start at 100 or another one to start at 200. And we want to graph the graphs for that. So here your R is positive and your K is positive, so we actually know what this is going to look like. We know the steady states right away. So yeah, logistic problems should go by really fast. So one, if you want the steady states, you know it's going to be n equals 0 and n equals 300. Right? Your R is positive and your K is positive. When you go through the work, it's always going to be 0 and the carrying capacity. The inflection points is always the carrying capacity over 2. So the carrying capacity was 300, so this is going to be 150. 2. the stability graph, in this case, is going to be an inverted parabola that goes through 0 and the carrying capacity, and the maximum will happen halfway there. So that's your inflection point. This is the steady state. This is the steady state. The K is always the stable steady state. It's the carrying capacity is what the population normally tends to, and the 0 is always the unstable steady state. So anyway, that's the stability graph. 3 we skip as always. 4 get to the solution. In this case we're calling it N. So 0, steady state, 150, inflection point, 300, steady state. My initials are 100 and 200. So the 100 would look like this, the 200 would look like that. So you see the logistic pretty quickly, minimal computations because you know how it's going to look. Once your R is positive and your K is positive, you have a template. You just go in and you fill in the numbers.
So it never changes?
Once your R and K are positive, they'll always look like this.
What if it's not?
Then it looks like something else, but you are not going to get that.
Can K be negative?
K cannot be negative,
Yeah.
because for populations that just doesn't make sense. The natural state is a negative population, it doesn't happen. Your R can be negative though, and the way that would change is this parabola would flip upside down. So the stable one would be 0, and then the unstable one would be this.
Here's part B for now.
Yeah, so that was part A. Part A was to get to the graph. Let's see. Sketch the curve, right? So this is part A, to sketch these two curves. Then there's part B. For each initial condition described, determine for what population size the growth rate is a maximum. Right. Growth rate is a maximum means the tangent line has maximum slope. So for this one, you can sort of look at it and know it's going to happen here. That's where the steepest slope is. For this one, the steepest slope happens right at the beginning, right? And then it starts to get shallower. So for 0 equals 100 max dn dt occurs at n equals 150, your capacity over 2, right? This is when your population hits 150, that's when it's increasing at its maximum. And for 0 equals 200 max dn dt occurs at n equals 200, right? It starts out as its maximum growth rate and it just decreases from there on. So part B just required you to sort of think of the tangent lines and where is the steepest slope happening.
Is this how they ask the question on the final? Or like it's different?
Question on the final for a logistic. This would be typical, except they probably wouldn't ask something like part B. It's possible, but it's less likely.
Would they want you to go through the calculations of the steady state, or could you just write a map?
No, if you write this out, I'll be fine with it. I'm grading the final anyway, so it doesn't matter. Problem 13 is good practice for a final. Yeah.
Can we go number 12?
Yeah.
Yeah, what would they ask
Very
for?
That was crazy. Sorry.
Problem 7 is harvesting. That's good practice for a final. And problem 12, let's look at that. by the way, good practice for a final also means good practice for a test, because I try to ask my questions to look like things you might face. So this says the logistic equation can be solved using separation of variables. We don't do it because it needs an advanced integration technique. But they're saying that n prime equals Rn times 1 minus n over k has solution n is equal to k over 1 plus c e to the minus rt. They're just saying, in theory you could solve it, and this is what the answer you get, and one thing you want to do is to verify that this is a solution. Which means if I plug that guy into the differential equation, it makes sense. This is just like what we were doing on the first test. So assume n is that, find its derivative to see what expression we get, and then find this side to see what expression we get, and they should be the same.
They were asking for a value of c, right?
Yeah, part
The-
A, I thought they were asking for.
Yeah, but
No.
constant C.
Part A says for any c, verify this formula gives a solution. So you don't have to find c. In general, you can't find this guy unless they give you an initial condition.
Yeah.
So then your n prime would be, well, I probably rewrite it so I can avoid the product rule. And so n prime would be minus k 1 plus c e to the minus rt to the minus 2 times minus rc e to the minus rt. So this ends up being rk e to the minus rt all over 1 plus c e to the minus rt squared. RCK. Right, did I do that? So this is what the left-hand side should look like. And now let's look at the right-hand side. The right-hand side says I have Rn times 1 minus n over k. So this means I have r times, I'm assuming n is this thing. So it's rk over 1 plus c e to the minus rt times 1 minus k over 1 plus c e to the minus rt all over k. All that's going to happen there is the k's are going to cancel. So we have rk times 1 plus c e to the minus rt times 1 minus 1 over 1 plus c e to the minus rt. Here I can create the common denominator. Right? This I can think of as 1 plus c e to the minus rt over 1 plus c e to the minus rt, and then I subtract 1, so that leaves me in here with c e to the minus rt. And now I would just multiply those. So this gives me RCK e to the minus RT divided by this times this is the same thing, so that's just squared. And I'm like, that's that guy. That's equal to the left-hand side. So that's verified. Let's make a dramatic effect. So yes, this is actually a solution, and notice that the C doesn't matter. It's the same. C could be any number and it would still be the same. And in part B, show that if n0 equals this, then the value of c is given by that. So n0 equals naught implies that c is equal to k over n naught minus 1. Since n is equal to k over 1 plus c minus t. Right. Then you just plug in the initial condition, right? When your t is 0, your n should be n naught. So this means that n naught is equal to k over 1 plus c e to the 0. So this means n naught is equal to k over 1 plus c. This means that k over n naught equals 1 plus c. This means that c is equal to k over n naught minus 1. There's a part C to it.
There's D2.
Really? I didn't even see it.
In our discussion of logistic, we showed that when a population starts out below its carrying capacity, it increases to reach its maximum. When it reaches half its carrying capacity, the population reaches the maximum when the population size reaches half its carrying. The rate of increase. Yeah. Show using 5.8 that this occurs when t is that. So show n prime is a max when t equals ln 0. So n prime equals is maximum when, how do you know if a function attains its maximum? It attains its maximum at some t value if what happens? When do you get a maximum of a function?
Decrease, that's decrease.
Right, if the derivative is 0 is the first condition, right? Well, it's a critical point, 0 or undefined. So this means that n double prime equals 0 or undefined. And at the same time, n double prime is negative, positive, to the left of t0, and n double prime is negative to the right of t0. All I have to do is show that this happens when your t0 is equal to this. So I know that n prime is equal to Rn equals to Rn minus Rn squared over k, which means n double prime is R minus 2Rn over k. So for max, we have that R minus 2 Rn over k should be equal to 0. This means R should be 2Rn over k, which means I can cancel those R's. Your n would have to be k over 2 over actually knew that. We actually knew this already. We didn't have to do all this. And I think the question said it. See, that's why I should read the problems. So, what did we have? It told us that our n is equal to k over 1 plus c e to the minus rt. And we know that the maximum growth rate occurs when your n is this. So all I do is I plug it in. So for max n prime, we have that k over 2 is equal to k over 1 plus c e to the minus rt. Which I can divide by k to get this. Which means I can flip both sides to get that. Which means 1 is equal to c e to the minus rt. Which means 1 over c is equal to e to the minus rt. Then you ln both sides. And we have ln of 1 over c is equal to minus rt. But remember, ln of 1 over c is just minus ln c. So your t ends up being ln c over r. Yeah, this we actually do. But I mean, if you like proving it for fun, like I just, oh, let's just do this. You could have done it. Repeat the calculation using the hell no. Okay, so part B just asks us to actually plug in a value for R and K and blah blah blah, which they gave you in a previous table. It's just plug and chug at this point. Right. Any other questions? Quickly. From what? 3. Problem 3.
And then also 14C.
At the same time.
Yeah. I think I might have been confused
So,
on the wording or something.
We'll just do 3 and 14 and then we're not this for almost an hour now.
I just wrote a question mark next to it.
You have to deliver 90 milligrams per hour, which may keep the strip on keeps the stabilized at 300.
I just don't understand how to do that.
So,
Exactly.
no,
It's a backwards 7.
Let's see what we said with 3. Okay, in 1997, the USA's population is 97.5 million. Mexico's population, no, Mexico's 97.5. US is 268. We're using the Malthus model. And the growth rates from table 5.1. And when will they be equal and what is their common size is the question. So we go to table 5.1, which gives us the birth and death rates for each country. So from table 5.1, we realize the following. The R for the US is birth rate minus death rate. Remember, that's how we computed it. So it's 14.4 over 1,000, because they said per 1,000 in the table, minus 8.8 over 1,000. which is, what's the answer to that?
0.0056.
0.0056. The growth rate for Mexico would be the birth rate 25.49 over 1,000 minus the death rate 4.91 over 1,000. That's equal to 0.02058. Okay, so now the question is, when will the populations be equal and what is their common size? So this means we want US population to be equal to Mexico's population. Using the Malthus model, this means that 2.268 e to the 0.0056 t, I want that to be equal to 97.5 e to the 0.02058 t. Remember, this is because the Malthus model says that n prime is equal to Rn. And when you separate the variables, this gives you that n is equal to n naught e to the Rt. Right? So that's what I'm using. The initial population times e to the growth rate times t. Right? So I do that for the US and Mexico, and I want to solve for the time when this will happen. When will these actually be equal? All right, how do I do that?
Take ln size. Can you do that? I did ln 268 plus ln of e to the thing equals to ln.
Yeah, you can take L on both sides, but you'd have to remember what you said to put a plus in between them, right? So you could take ln on both sides, one way to approach it. And you'd have, there are several ways to approach this, but that's one of the ways. Probably the way that I would have done it was to bring all the numbers over on one side, bring all the e's on the other side. So like 268 divided by 97.5 equals e to the 0.02058 t over e to the 0.0056 t. What you said was correct, but I feel like this would be sort of more natural. 268 divided by 97.5 is what? 2.74. Huh? And this guy, you're dividing something in the same base, you just subtract the powers, right? So it's just e to the 0.02058 minus this is what? 0.01499 t. And at this point, write ln both sides. So
You ultimately do the same thing.
yeah, you have to ln, but you know, I can see a lot of algebra mistakes when people do it here. They put ln of this times ln of that, or silly things like that. Not many people would remember to put a plus sign in between them. That's why I don't want to risk telling you to do that with something. I'd rather you separate it first and then ln. So t would actually be ln of 2.7487 divided by 0.01499, which is 67 point. Oh, you just stopped at one decimal point. Okay. So this is the when. That's the when they'd be equal. The common size means you just have to plug this time into either one of these numbers. So I can, common size is equal to, let's say, 268 e to the 0.0056, and for t I'm going to plug in 67.5. And this is in millions. And what is that?
291.
291?
3. 91. 291 million. 300.
3. Roughly. And problem 14. Okay, differential equation has the same type of 5.6. Okay. Just alright, in the problem psychology, so-called compartment models, for example, suppose a body excretes or metabolizes 30% of a certain antibiotic each hour if a patient is given continuous intravenous dosage of 75 milligrams per hour. That's a rate. Explain why the amount of Y in the antibiotic indicator satisfies this guy. So the idea is, it's sort of like a harvesting model. We know this makes sense because it's a harvesting model. The R is equal to minus 0.3 since 30% is gotten rid of. Per hour. The H is, technically it's a minus 75, which in our general formula would make it a plus 75, since this amount is added per hour. So it's a constant addition, so the rate of change is 0.3, and this is your H. When you plug it in the harvesting model, you end up with that equation. So it's the amount of what rate it's changing at naturally, and you're adding this from an external influence. It's just the harvesting model. And so you get that differential equation. Find the limiting value of the amount of antibiotic in the patient's blood. Justify your answer using qualitative methods. Note that you should take y of 0 equals 0. Why would you start at 0?
You don't have any drug inside.
Right, because naturally you don't have it. So in the beginning you don't have the drug and then we inject you with it. So you have 0 amount of the drug in your bloodstream before we actually inject you. That's why y of 0 is 0. But they want us to use qualitative methods. And the story is the same old, same old. The first one, you find steady states and inflection points. Steady states, you set minus 0.3 y plus 75 equals 0, so your y is equal to
250.
250. This is a steady state. Inflection point, your y double prime would be equal to minus 0.3, which is not 0, so no inflection points. Now we draw the stability graph. Y versus y prime. It's a straight line with negative slope. Vertical intercept is 75. Horizontal intercept will be the steady state, which is 250. Arrow to the right, arrow to the left. This is a stable steady state. Step 250. That's our steady state. Assuming y of 0 equals 0 because you had none of the drug in your bloodstream at the beginning, so that starts at 0. And what would it look like? Concave down, increasing. So that's what the drug would behave. The amount of drug in your bloodstream would behave like that. And so when they ask the question, what's the limiting value? This implies the limiting value. As time goes on, there's a limit to how much it will stay in your bloodstream. It is 250 milligrams. Right? You will never get more than that with this particular drug. Why is being able to compute this important? Well, sometimes drugs can be dangerous in high doses, so you want to make sure it doesn't pass a certain dose. So if 250 milligrams was, beyond that would be lethal to the patient, you wouldn't want to give them more than 75 milligrams an hour. And that will actually tell you how to judge the dosages you give for medication.
Or if you smoke something, then you have a drug test.
Yeah. Yes. In less legal ways, how long before a drug test can I smoke weed? Okay. So in part C, right, you'd have to figure out how long does it take my body to expel the weed, you know, how many milligrams is in, yeah, okay. All right. That's some high motivation. You learn all this calculus just so you know when to smoke weed. Damn it, do something better with your life if you're going through all that trouble. Okay, all right. Suppose the antibiotic is fed in liter bags containing 500 milligrams of antibiotic. They're replaced when they are empty. At what rate should the drip rate be set so that the long-term patient will have a steady flow of 300 milligrams of antibiotic in his blood? In other words, they're asking you to change the 75. Basically is what they're asking. They said, we want the steady state now to be 300, right? How much milligrams per hour should this person get? At what rate should set? Yep. So basically you have the y dt is equal to minus 0.3y plus r. And we want to find that r so that our steady state is at 300. Well, this means we need minus 0.3y plus r equals 0. This implies your y is equal to r over 0.3. This implies, this would be, by the way, your steady state. Right. So we want r over 0.3 to equal 300, which is 90. And that's sort of it. If you want the steady state to be 300, you should be giving this patient 90 milligrams per hour. And if you have 500 milligrams of that, 500 milligrams per bag, this will sort of actually also tell you roughly how often you have to change the bag, right? Because every hour you'll finish 90 milligrams, right? So that'll actually tell you, remind you when you need to change the bags. So one bag can take you more than an hour. Well, it can take you
A
few hours, about 6 hours. So you know you'd have to change this bag every 6 hours and make sure you set it to give the patient 90 milligrams.
No, but there's 500 milligrams in the bag, right?
Yeah.
And they want to give it at, right, but they want to know how many milliliters they want to give per hour,
Yeah.
right? So you're giving,
Yeah.
yeah, okay, yeah.
So if you take 500 divided by that, I think that's a typo and should be milligrams. But 500 divided by 90 is how many bags you need, how long you can keep a bag. Yeah.
The milliliters is like 0.5 milligrams in a milliliter, so you have to give 180 milliliters an hour, right?
Yeah. Okay. So, all right, you can pass your homeworks up to the front.
Thank you. You taught your mother something.
What happened?
No, it was my homework and they just taught my mom how to send it to me.
Technology. So, chapter 6 is relatively a long chapter. We're definitely not going to finish it today, but we can at least start off in the beginning. Set up some basic background stuff. So remember I told you had to remember how to do systems of equations. You're going to need to do that, so I'll probably review that for a little bit and see how far we get. Chapter 6. We're dealing with systems of ODEs. In particular, we'll be dealing with systems that look sort of logistic, but that will come later. For now, I want to make sure you can actually solve systems of equations. You guys remember what a system of equations are? It means you have several equations that you want to consider at the same time, and you want to find a solution that works in all equations at the same time. You call this a system of equations. It's very important that we remember how to solve linear systems of equations. So for example, x plus y equals 3, and 4x minus y equals 2. If you had that system of equations, I need to find a solution that works in both equations at the same time. Right? Tell me an x and y value that will, when you add them, you get 3. When you take 4 times this minus that one, you get 2. There are a couple ways you learned how to do this when you did it in algebra. One was called the elimination method. The other was called the substitution method. Let's do elimination first. How would that work?
Multiply the top one by 4 so you can eliminate that.
You have the right idea, but you're thinking too.
The x and a y cancels out already.
The y's will kill each other already. You don't really have to multiply them. The idea is, it's called elimination because you want to eliminate one of the variables. So what you do is you can add or subtract equations so that one of these variables die. Now, if the numbers would have to be opposite if you want to add them, right? So here I can add the y, this equation to that equation, and the plus y will kill the minus y, right? If I wanted to eliminate the x though, what I could have done was multiply this equation by -4, and then I can add it to this and kill the x, right? But that would be working slightly harder because we get the y's for free. I can just add them now. I don't need to multiply. But in general, that's the idea. You want to multiply one or both equations by something that makes one of the variables the opposite, and then you add them together to eliminate that variable. That's why it's called elimination. So here, this is equation 1, that's equation 2. What we are going to do here is take equation 1 plus 2, because I realize that will actually eliminate the y. So I add these guys. So x plus 4x gives me 5x. plus y minus y gives me no y. 3 plus 2 gives me 5. And so here I can get that x equals 1. And so now that I know x equals 1, how do I find the y? Right, once I find one of these guys, I can plug it into any one of these equations. I'll choose the first one because the numbers are nicer. And so in 1, this means that if I take 1 plus y, I get 3. This means y equals 2. So xy equals 1, 2 solves the system. Right? And you can check if your x is 1 and your y is 2, 1 plus 2 gives you 3. If your x is 1 and your y is 2, you get 4 minus 2 gives you 2. Right? So I found x and y that works in both equations at the same time. Right? And this is how you solve a system of equations. One way is by elimination. There's another way. Substitution. Remember how that one works? Yeah.
You can solve for one of the variables and then plug it into the other equation.
Right. You solve for one variable and substitute that expression for that variable in the other equation. So that's how that works. So let's do the same example. X plus y equals 3, 4x minus y equals 2. In equation 1, I can solve for any one really. I can solve for x, for example. And then substitute into 2. This gives us, I should probably solve for the y, it'll be nicer. Doesn't matter. It's not like crazy amounts of arithmetic here, so it's just, we don't have to avoid it. It's not going to be much different. Right? So I replace the x with what it's equal to. And now I just get one equation with one unknown. There are only y's here now, so I can solve for that. This means 3 fourths 12 minus 4y minus y equals 2. So this means 5y equals 10, which means y equals 2. And 1, this gives us x plus 2 equals 3. This implies x equals 1. And we get the same solution. Do you remember this?
Yeah.
So either method you use, I don't particularly care, just know how to solve an equation. But yeah, that we knew how to do like 3 semesters ago. Let's make it a little more interesting. Let's increase the difficulty just slightly, ever so slightly. And then we're going to increase it like by this much. If not this class, next class. But this type is very important for you to know how to solve. How do you do that one? All right, ideas?
Can you just set them equal to each other because we both know that they're equal to 0?
But then you'd have one equation with 2 unknowns.
Not true.
Doesn't help enough.
So just Spread it out. Expand them and add them or substitute.
Expand them, how would that help? I'd get 50x minus x squared minus xy.
Or we can.
One would have an x squared,
We know
one would
x,
have a y squared.
X has, let's say we can set x equal to 0 there because we know in one of the equations, or y equals to 0 because we know one of those two values would have to be 0, right?
Yeah.
So, and then just plug it into the other one.
That is actually a good approach. Say from 1, what do we know has to be true? Well, x equals 0, or 50 minus x minus y must be equal to 0. Right? At this time, this equals 0 means one or the other has to be 0. So now this guy becomes two cases, right? What if this is true? What would happen? And what if that is true? What would happen? And we deal with them one case at a time, right? If x equals 0, then what can we say?
That y is equal to 50. Y is equal to 50.
Then it wouldn't matter what y was equal to because, right, once you multiply
It wouldn't matter.
Wouldn't matter.
You're like in the grand scheme, right?
What would happen? Would be 50.
Yeah.
Are you sure?
Guess 50
Look at
minus-
equation 2. If x is 0 and y is 50, does it work?
Why can't you
No.
go to 2?
It doesn't work.
Right.
That's your problem. You're only isolating everything to equation 1. We need both of them to be solved at the same time.
Let's try the second.
So let's set the second value because you.
Not necessarily the second. Right, what did we do in the substitution method? We took something we knew from 1, and then what did we do? We applied it to 2. Because whatever situation works in 1, I have to make sure it also works in 2. So that's what I did. I know for 1, this has to be true, but how is 2 going to behave? So what I'm going to do is I'm going to plug that situation into the second one. Right? If x equals 0, then I worry about equation 2. Right? Whatever equation you start off with, use the other one to finish, because you need both of them to work together. Right? So if x equals 0, equation 2 becomes and what does that mean?
Y is that.
Y is 0 or y is 200. So from here, I get actually two solutions. xy is either 0, 0, right? X is 0 and y is 0. Or xy is 0, 200. Right? When x is 0, y is either 0 or 200. So I have two pairs of solutions here. And then I worry about the other situation. So this is what happens if x equals 0. These two are solutions. If the other thing happens, 50 minus x minus y equals 0, how do I deal with that situation? Remember, we got this from equation 1. So I'd want to apply it to equation 2 in some
So you just pick one of the variables, set it equal to the other. So like you can say y is equal to 50 minus x or the other way
Sure.
around.
Say y is equal to 50 minus x, and then you plug that expression into 2. Although, I probably prefer to solve for the other one. X is equal to 50 minus y. Why would I want to do that? Well, sometimes you have to look at what will make your life easier. If I replace this guy with a binomial, I'm going to have to multiply out a 2-term thing by a 3-term thing, which is not nice to do. So I want to leave this guy as one variable and then multiply out. That would make my life easier. So in 2, what would happen? I would just have y times 200 minus 2 times this x value. And set that equal to 0. This means I have y times 200 minus 2 times 50 is 100. So that's 200 minus 100, which is 100. Minus 2y, this plus 2y minus y is just plus y. So this would mean y equals 0 or y equals minus 100. And what does that mean? What are my solutions?
You know, you have to plug it in to get x.
Yeah, we need to figure out what is the x value. How do I know the x value?
Plug in one of the y's.
Here, I know x is 50 minus the y. So if y is 0, this would mean my x is 50 minus 0. So x is 50. So here I get the solution 50 comma 0. Over here, x would be 50 minus 100, because it's 50 minus y. So this gives us 150, which gives us another solution of 150 comma minus 100. So ultimately, all the solutions to this guy, we actually have 4 possibilities. xy is equal to the origin, or 0 to 100, or 50 comma 0, or 150 comma minus 1. The kinds of equations we're going to be solving in this chapter are far more similar to this one than the first one. I just wanted you to get the idea of the back and forth play that you have to do, right? You figure out something that works in one and make sure it works in the other one. That's going to be a constant theme for going through this.
All 4 are possible solutions to it.
Yes, all 4 are possible solutions. And we're going to get into a situation where these guys are going to be our steady states that we have to worry about. But we still have some more background before then. Do you understand what happened here? Okay. So this is just another background material, and then we're going to jump right into the models that we want. So I'll just end with this example, and then next time we pick up. With the specific stuff we want to get to. So we're basically going to do this one at a time, and then later we'll do 2 equations together. So 50 minus x minus y looks just like what we had before. So for each of these, I'm going to graph this line and then figure out what is the sign of this expression in each of the regions that develop. So let's do part 8. How do I graph that line quickly? What kind of curve is this?
Linear.
It's linear, it's a straight line. All right, how do I graph it? Huh? could get into y and x plus b form, but we're in a test, we have tons of other things to do. Graph it quickly.
If these are the wider stuff, then it's negative slope.
Yeah.
That's how you guys graph quickly.
It's just like a y equals x graph, but the intercept's at 50 and it's decreasing.
That's nice.
Yeah, but how would you know that?
You looked at
Well, what if we're not all geniuses like you? Sheesh. Find the intercepts is the quickest way. Plug in 1 equals 0 at a time, right? If x equals 0, what is your y? It's 50. 50. If y equals 0, what is your x? 50. That's the line, right? You know, if y equals m is supposed to be a negative slope. You try to measure it, you move to the right and then move down. No, we're not in algebra anymore, right? Find the intercepts. Plug in one variable equals 0 at a time. Solve for the other guy, put it on the axis. Right? That's the way you draw it quickly. Straight lines, all you need is 2 points to draw a straight line. So you find the 2 easiest points there are to find, right? When one of the guys is 0. Okay. Now the question says, what is the sign of the expression, right? So the sign of this expression, now you notice that there are 2 regions that happen, right? There's region 1, that's on this side of the line, right? It cuts the entire plane into 2 parts. There's region 2 on this side of the line. What is the sign of this expression in each region? How would I figure that out? Plug in a point, right? Take any random point in this region, say 0, 0, because that's pretty easy, right? If I plug in x equals 0 and y equals 0 into this expression, what do I get?
50.
I get 50, right? If x equals 0 and y equals 0, then 50 minus x minus y is equal to 50, which is greater than 0. So in this region, the sign of that expression is positive. What about in region 2? How do I figure out the sign there? Pick a random point, right? What point do I know is in there? 50, 50, for example, is a point in there. And then you say, if x equals 50 and y equals 50, then 50 minus x minus y is actually minus 50, all right? Which is actually negative. And so the sign on this side is negative. And one thing I want to emphasize here, this is not a coincidence. This sort of thing happens all the time, meaning, i.e., the sign switches when you cross over the line. Right? Once you have some curves cutting the plane into several pieces, then if you know if the sign is positive on one side, it'll switch if you go to the other side. Right? That's just how it will work. So that's not a coincidence, and that's going to be something that's important and will come back later, but that's just something you need to know. We'll use that a lot later. All right, any questions on this so far?
Is that true for all curves or just linear ones? Like if
It'll be true for all curves. If you cut it in 2 parts, and if you bring everyone to one side, look at that expression. Whatever sign gives you on this side, it will switch when you jump to the other side. Let's do the same thing for B. Right? And hopefully we can do this really quickly. So how do we graph this? Plug in 0 where? Which one would you do first? If x equals 0, what is our y? 200, so you go here, you plot 200. If y equals 0, what is our x? 100, so this one will go through 100. So that line would look like this. Put a random point over here, this is 0, 0. And this means I have 200 minus 0 minus 0, which is positive, so over here there's a plus sign. What's the sign over there? You automatically know it's a minus sign. Don't even waste your time computing. Once you jump over this line, it's going to switch. Right? Later on, we're going to be doing this where we're going to be testing the signs in regions, and it will greatly cut down on your computation if you just know, oh, if I jump over this line, that sign switches. It's going to be a useful concept. So that's it for now. We'll stop there. We'll pick up next time.